Okay, so in the last video we looked at how the speed of the wave on a string is related to the property of the string, right? Now, so the wave on the string is actually what? It's it's a type of a one-dimensional wave, or harmonic wave. Okay. So let's see, how can we represent mathematically such a wave? So mathematical representation of a harmonic one-dimensional, well, really other two-dimensional motion are also harmonic, so we shouldn't say that. A harmonic, oops, sorry, harmonic, so it's in U sinusoidal. SOIDF. So basically sine and cosine, right? Like you represent this harmonic motion or simple harmonic motion as, using sine or cosine function, and you could call those that kind of function as a harmonic function or a sinusoidal wave, okay? So sinusoidal, so mathematical representation of a harmonic sinusoidal one-dimensional traveling wave. Okay, I'm gonna start writing American style of traveling with one L, L-I-N-G, traveling wave. Okay, so how do we represent the wave? For example, even the wave on the string, basically. So let's say snapshot in time. Snapshot in time. This is given as y x t equal to 0, and that is just like a sine. Really just like how we did for simple harmonic motion, okay? A sine 2 pi lambda times x, okay? So, but remember this now y, right? This is the function of x and t here. So t at t equal to 0, okay? It's snapshot in time. So yeah, just if I were to just take a picture, wave is moving here, bim, if we take just one click here, a snapshot here, then we can represent that wave, that we can represent that wave mathematically this way, okay? So you guys already know a is the amplitude, right? So x is it's just the displacement displacement of the propagation. Lambda is the wavelength, right? Okay. So general expression is given as expression. I don't know if you can see this here. Let me check my video. Okay, you can see it. Oops, you can see it, but I'm gonna maybe write it up. Okay, I don't want it to be cut. Then I have to again, take a picture and then upload it. So, general expression of a traveling wave is given as y as a function of x t equal to a sine 2 pi by lambda x minus 2 pi ft. Oh, this part looks familiar, right? From simple harmonic motion. Okay. So this is just the general representation, general expression for representing a traveling wave, okay? in both, as a function of both the position or the displacement and the time. Do we have to really use sine? I mean, could we not use cosine? You could really use cosine, so there it's not just sine, right? Because cosine can also represent, a repetitive motion. Okay, so you could also have just use cosine instead of just sine function here. All right, so let's look at let's do a little bit of example here. So, actually, you know what? Before we do the example, let's look at some of these. I'm going to erase this part here. So let's look at some of these examples, other examples. So, right, the wave on a string was an example of a one-dimensional wave, right? I have an example of two-dimensional wave here, outgoing water wave, you guys see here, right? Outgoing, so ripple here, right? So this is a two-dimensional wave, okay? Kind of looks like it's in a, I don't know if you guys are able to do this. This looks like a line, one dimension. That looks like something you can put in a plate and eat. It looks like a two dimension, okay? That's the easiest way to say it. Really, it's like a circle, right? If you have a circle, if you have, two dimension, okay? So that's a two-dimensional example of two-dimensional wave. Here is an example of three-dimensional wave. So three-dimensional wave is a spherical wave here, basically. So before you had a circle, now you have a, just like a circle, now you have another circle on that also. So like this circle and you have like this circle, that really makes a whole sphere, right? Like that's like a soccer ball basically, right? Can you see that? So you may be wondering, like, where can I see such a kind of a wave where the wave looks like a soccer ball? I mean, not exactly like a soccer ball, but we can represent some of the waves that are spherical wave, represent as a spherical wave. For example, let's say when there is an earthquake, what happens, right? The wave that is propagated, we could, take it as a spherical wave. Okay, so assuming if this was, the earth. Oh, okay. So here is, I'm going to draw this one. Here is an example. Given a snapshot at t equal to 0 for a wave with speed v equal to 8 meters per second traveling right. Okay, so I'm going to make a wave here. Very good. Oops, this is not damping. Okay, that might just diagram looks like a damped, not damped. So, that also, okay. That's same, okay, so not damping. You can make more, but I'm going to leave it here. So x, this is x in meter, and this is y in meter. At 0, 1, 2, 3, 4, 5, and so on. 0.01, and this point here corresponds to 0.02, and then the other point at 0.03, and so on. We have same thing on the opposite side here, and the negative y-axis minus 0.01, minus 0.02, kind of, well, I'm going to move this, guys. This is supposed to be very good scale, but my diagram is not to scale, guys. So this peak should be at the same height as this, okay? So let's so make it minus 0.02, okay? And then minus 0.03 and so on. Alright, so you want to find, amplitude A, lambda, wavelength, F, frequency, time period T. I'm going to give you guys something here. Useful equation. This is not only the useful equation, but one of the useful equation is B equal to F into lambda, where B is the speed of speed of wave, F is the frequency, and lambda is the wavelength. Okay, so this is one of the useful equations. So try to work on this. Take a couple of minutes and see if you can find out this information from this data with the given information. Okay, so please try this out. Okay guys, so are you able to get some of this information, if not all? Okay, so I'm gonna leave this graph and erase this part because I need space to work here. Alright, So the first and foremost thing is always in physics, we want to write the given information, right? Given a snapshot at t equal to 0, say 0, it says only 0, so let's write just 0. For a wave with speed v equal to 8 meter per second, traveling right. And then this is the graph we have, and we are asked to find a equal to what, lambda wavelength equal to what, f frequency is what, and then t period is what. Okay guys, so the first and foremost thing is we are given v, but we cannot find, we don't know what is lambda yet, right? So let's see what are the information that we can get it right away from this graph. So remember, how can we represent this wave mathematically? We can write what? Okay, I'm going to erase this part here, okay, question part here. Y x t equal to what? A sine 2 pi by lambda times x minus 2 pi ft. Okay, this is the general equation, right? So it's the general equation now. So first, so the thing we really have here is we don't know anything about the f here, right? We cannot say anything from this graph here. However, we do know a, right? We can look at the a is what? The maximum displacement, right, of the particle here. So what's the maximum displacement here is from this point all the way to here. So this distance is our amplitude A, okay? So that is given as what? 0.02 meter, okay? That is straightforward. Now we can we find lambda? Lambda is a wavelength. Wavelength is what? If we go back to the, how we define lambda is basically the length covered by wave in one period, right? So if we look at the distance that's covered by this wave in one period, or the distance traveled by a wave before it starts repeating, maybe that will be easier for you to visualize. So this wave starts here, goes like this, goes down, goes, and then boom, right here it finishes, again from this point it starts to repeat, okay? So how much distance did it travel from this point 0 all the way to up to here before it starts repeating again? So 0, 4, right? So 4 minus 0 gives us 4 meter. That's our wavelength, okay? Alright, so we know now the amplitude, we know lambda. So we should be, can we find t just from here? Period t, or even frequency from this graph here without doing anything? Probably not, right? So what do we need to do is this. So now we know v, speed of the wave, v is related to the frequency and wavelength as f times lambda, right? Okay, we are given v in the question. It says that the wave is traveling at 8 meters per second. We have found lambda, now we should be able to find f. Okay, so f is just v divided by lambda, which is what? v is 8 meters per second, lambda is 4, so that gives us 2 hertz. Okay, f is 2 hertz. And now you guys know, since you guys know f, you should be able to find t equal to 1 over f, which is 1 over 2 second or half second, right? Time period is half second. Okay, so this is how you do this kind of problem. Excuse me. okay, this is all for this video.